Hello, welcome to Not for Exam, and I am your host Sujit, and we are going to talk about diffraction. In general, diffraction refers to flaring out of light across the edges, and secondary wavelets at the edges are responsible for flaring out of the light. Let's see a typical example of single slit diffraction. If central maxima has intensity Im, then intensity at first side maximum observed is approximately 4.5% Im, and second side maxima has intensity approximately 0.83% Im. Let's find position of first minima. For two pairs of wavelets at b by 2 distance, path difference delta x will be equal to b by 2 sin theta must be equal to lambda by 2 for destructive interference, and there will be always a pair corresponding to any point on the slit for which distance is b by 2. Therefore, for b by 2 sin theta is equal to lambda by 2, or b sin theta is equal to lambda, or at theta is equal to sin inverse lambda upon b, all pairs interfere destructively, which will be the position of first minima. And as b increases, angular position of the first minima will increases, and for b close to lambda, theta is close to 90 degree. That means central maxima is spread over entire screen. And if we take pair of two wavelets at a distance b by 2n, then we get position of nth minima, where b by 2n sin theta is equal to lambda by 2, that is b sin theta is equal to n lambda, or theta is equal to sin inverse n lambda by b, which is the angular position of the nth minima. We are going to discuss intensity in single slit diffraction qualitatively. We can divide slit width b in n equal zones, each of width delta y, such that n delta y is equal to b. Phase difference between two wavelets at a distance delta y will be delta phi, that is 2 pi by lambda into delta y sin theta. Also, let due to each zone, delta e is the individual amplitude at p. At theta is equal to 0, delta phi is equal to 0 between adjacent waves at delta y distance apart, and the net amplitude will be E maximum, as can be seen from the phasor diagram. For n tending to infinity and delta y tending to 0, phasor diagram turns into a continuous curve, and two adjacent waves can be assumed at a distance delta y tending to 0. At any general angle theta, delta phi is equal to 2 pi by lambda into delta y sin theta, and phasor diagram can show the resultant amplitude as shown. For delta y tending to 0 or n tending to infinity, phasor diagram turns into a continuous curve. At b sin theta is equal to lambda, or theta is equal to sin inverse lambda by b, there is a minima, and phasor diagram turns into a closed circle showing the zero resultant amplitude. Similarly, h for b sin theta is equal to n lambda, or theta is equal to sin inverse n lambda by b, phasor diagram turns into complete circle showing zero resultant amplitude. We are going to discuss intensity in single slit diffraction quantitatively. Intensity at an angle theta is equal to Im sin alpha upon alpha square, where Im is maximum intensity at theta is equal to 0, where alpha is half phi, that is half 2 pi by lambda b sin theta, or pi by lambda b sin theta. Given phasor diagram at angular position theta shows the phase difference phi between the two extreme waves, where phi is 2 pi by lambda into b sin theta, and where alpha is equal to phi by 2. By geometry, arc length r phi is equal to maximum value of amplitude Em, which is at theta is equal to 0, and amplitude at angle theta, E theta is equal to 2r sin alpha, that is equal to 2 Em sin alpha upon phi, or Em sin alpha upon alpha. Therefore, intensity at angle theta is equal to Im sin alpha upon alpha square. We are going to discuss diffraction by a circular aperture. For circular aperture of diameter d, first minima occurs at an angular position theta, given at sin theta is equal to 1.22 lambda by d. In comparison to single slit, extra factor of 1.22 is due to circular geometry of the aperture. Resolvability of two distinct points is limited due to diffraction. To resolve two distinct points or point objects which have very small angular separation, their diffraction maxima should not overlap so much, which can be understood from the following examples, showing the situations when two maximas are not resolved, just resolved, and fully resolved. For this, Rayleigh criterion quantitatively gives the relation for resolvability or resolving power. For angular separation, theta r is equal to sin inverse 1.22 lambda by d. Central maxima of one coincide with first minima of the other. Since theta is very small for the used typical cases, therefore theta r proportional to lambda, or theta r proportional to 1 by d. It can be seen from the above relation that resolving power is more for smaller lambda. We are going to discuss diffraction by a double slit. Diffraction by a double slit can be easily understood by the superposition of double slit interference pattern with single slit diffraction. The double slit interference for slits opening a very less than lambda and slit separation d, the intensity at angular position theta is given as I is equal to Im cos square beta, where beta is equal to half 2 pi by lambda d sin theta. And for single slit diffraction for slit width a, intensity at angular position theta is given as Im sin alpha upon alpha square, where alpha is equal to half 2 pi by lambda into a sin theta. And by superposition of the above two, we can relate that intensity at angular position theta is given as I is equal to Im cos square beta into sin alpha upon alpha square, where beta is equal to half 2 pi by lambda d sin theta, and alpha is equal to half 2 pi by lambda a sin theta. Also, we can find number of bright interference fringes within central peak of the diffraction envelope. For first diffraction minima, a sin theta is equal to lambda, and for nth interference maxima at angular position theta is given as d sin theta is equal to n lambda. Therefore, n is equal to d upon a, and total number of bright interference fringes within central peak of the diffraction envelope is equal to twice of greatest integer n. We are going to talk about diffraction gratings. In diffraction gratings, there is a dense array of many slits or rulings in the order of 1000 slits per millimeter. Let's take a look at a typical example of diffraction grating having slit width a and slit spacing d, and n is the number of rulings. Typical intensity plot and corresponding bright fringes are as shown. Now take a look at the following diagram to find the position of mth maxima line. For mth maxima line, path difference between waves from two successive slits must be equal to m lambda. Therefore, path length difference delta x d sin theta will be equal to m lambda for mth maxima line. And to find the location of first minima, we can use same reasoning as that for single slit if number of rulings n very large. For first minima, nd sin theta is equal to n lambda, and for theta very small, theta is equal to lambda upon nd, gives the position of first minima. Therefore, half width of the center line delta theta hw is equal to lambda upon nd. Also, half width of the line at angle theta is given by the relation delta theta hw is equal to lambda upon nd cos theta. We are going to talk about grating spectroscope. The key component of a grating spectroscope is a diffraction grating. It diffracts incoming light into various directions, separating it into constituent wavelengths. Let's take a look at the given figure. If d is the slit spacing, then the position of mth order maxima lines is given as d sin theta is equal to m lambda, and for m equal to 0 or 0 order maxima, all components lambda overlap, and for m equal to 1, 2 and 3 and so on, we get first, second and third order maximas. Also, we can see that higher order lines spread more, as half width of the mth order lines is given by delta theta hw is equal to lambda upon nd cos theta. We are going to discuss dispersion and resolving power of a diffraction grating. Dispersion is the spreading of diffraction lines of different wavelength. It is measured as change in angular position of particular order maxima with respect to change in wavelength, and is given as d is equal to delta theta upon delta lambda. For a grating having slit spacing d, for mth order maxima at angle theta, it comes out to be d is equal to m upon d cos theta. Also, to resolve lines which are close together, lines should be as narrow as possible, and resolving power is defined based on Rayleigh criterion as lambda average upon delta lambda. And for a diffraction grating of n rulings, for the mth order spectral line, resolving power R is equal to n into m. Let's derive dispersion of a grating. For a mth order line, d sin theta is equal to m lambda. Differentiating it, we get d cos theta into d theta is equal to m d lambda. From relation 1 and 2, d theta upon d lambda is equal to m upon d cos theta, or dispersion d comes out to be m upon d cos theta. Now let's find resolving power of a diffraction grating. Since half width of the spectral line at angle theta is given as delta theta is equal to lambda upon nd cos theta, and dispersion d, that is delta theta upon delta lambda, that is m upon d cos theta. From the above two relations, delta theta d cos theta is equal to lambda upon n, that is equal to m delta lambda, or lambda upon delta lambda is equal to nm. Therefore, resolving power R is equal to nm. Let's compare between dispersion and resolving power. In the given three illustrations showing intensity pattern with respect to angular position theta, dispersion in grating C is greater than dispersion in grating A is equal to dispersion in grating B. That shows grating C has highest dispersion, and resolving power in B is greater than resolving power in A is equal to resolving power in C. That is, grating B has highest resolving power. We are going to talk about diffraction of X-rays. Wavelength of the X-rays is of the order of 1 angstrom. So, in X-ray diffraction for mth order spectral line, d sin theta is equal to m lambda, or theta is equal to sin inverse m lambda upon d. So, d should be in the order of lambda, otherwise theta will be very close to the center line. Also, fabrication of diffraction gratings of this scale is not easy, but crystal spacing is in the order of wavelength of X-rays. So, crystals can act as natural diffraction grating for the X-rays. Let's take a look at the following example. X-rays are incident on a crystal at an angle theta from a particular set of crystal planes having interplanar distance d, and then reflected by that plane. We can see that for reflection from these planes or for constructive interference in reflection, 2d sin theta is equal to m lambda. This is called Bragg's law, and angle theta is called Bragg's angle, which is the incident angle from the plane, not from the normal to the plane. Also, regardless of the angle at which X-rays enter a crystal, there is always a family of planes from which they can be said to reflect, and by applying Bragg's law, we can find crystal spacing of different family of planes, and by this we can know all the geometry of the crystal. So let's take a look at the following diagram to see the different family of planes and the interplanar distance in terms of crystal spacing A0. The Bragg's law discussed above is central to the field of X-ray crystallography, which is used to identify the atomic and molecular structure of the crystal. Thanks for watching Not for Exam, and we will see you next time.